So when we last left off, we were talking about the fixed bench magnetic particle testing that we'll be doing in lab or in industry. This would be typically in a back shop or a specialty shop that does NDT, where parts or components are sent there. So you're going to have a bench similar to this, like we have down in the lab, to be able to do what's called wet continuous magnetic particle inspection. That is, we will be suspending the magnetic particles in an oil bath. Okay, there's where the wet part of it comes in. And then we'll be applying it continuously while we're magnetizing the part, while we're running the current through either the coil or the part itself in order to create that field. Some of the other ones that we'll look at later are the dry methods, which is where you use a powder. And then there's also residual magnetism testing, which is where you run the current through, magnetize the part. The part's going to have residual magnetism at that, and then at that point you apply the particles, whether it's a wet or dry application. So, but we're going to be doing wet continuous. That's what these benches are designed. And remember, there's two ways that they can magnetize our part. The first is what's called longitudinal field, which is circular current. So we can run current through this ring that's on the bench. And that's going to, with that right-hand rule, the magnetic field being 90 degrees to the current flow, that's going to create a magnetic field that runs left to right in relation to the coil here. So it looks something like this. So once our part's magnetized, the current's going to be circular through that coil, that external coil, and the magnetic lines of flux or force are going to run longitudinally along the part, allowing us to find primarily transverse and angled defects, whereas longitudinal defects won't show up as much. The other method we have, or other direction, is to run the current through the part itself by connecting it to two electrode contact pads, one at each end, clamping it. We basically just clamp it between them, and the force is what creates that connection on those copper pads that are mounted to what's called the head stock that's on the left here, and the tail stock on the right, or the stocks. And that's when that current gets run through the part. So now our current is going to run along the length of the part. It's going to create a circular magnetic field in the part itself. And that circular magnetic field is going to allow us to find longitudinal cracks in various angles, but transverse cracks will not show up very well because that field isn't jumping across them as well. So those are the two main ways most of the time you're going to use to test parts. Now, these work well as long as our part is fairly linear. It can be clamped in those head and tail stock. But there are cases where we need to test circular parts or smaller parts that maybe have an opening in them of some kind. And so we have another method we can do, and that we'll call it circular part method, but it's using a non-ferrous rod to support our part. So what we mean by non-ferrous is something that's not iron containing. So that rod, for instance, here it shows a bronze or copper rod. Those are probably your most common ones that are used. We have pieces of bronze stock down there that we use for this. The bronze stock is clamped into the head and tail stock on each end. So it basically creates a conductor between the two pads there. And even though it's not a ferromagnetic material, when we run a current through a conductor, we do get a magnetic field that forms around that conductor, okay, for the time the current's flowing. Now, once you turn that current off, that conductor itself, in this case, that bronze or non-ferrous rod, will no longer be magnetized. But if you had a ferromagnetic part in close proximity, or in this case, where the rod is hanging on there, a circular part like a gear, or this sleeve that's part of a landing gear leg, it's kind of the alignment sleeve where the upper and lower leg come together. That steel part is going to magnetize because of that magnetic field that forms by running current through the non-ferrous rod. And so when we magnetize that, then we can also apply those ferromagnetic particles and look for cracks or damage to this. The other thing that this can do is, you can see they have a coil here. You can run current through the coil as well, simply using that non-ferromagnetic rod that non-ferrous rod, to support it, the object in the center of the coil. So again, we can run, when we run current through this rod right here, that's going to create circular magnetic fields around, around the outer circumference of the rod. And in this case, on this part, the magnetic fields would run, circular around the outside of the part. When we run the coil, that's going to run magnetic fields left to right. And so we can check both directions on a part like this that doesn't effectively, we wouldn't be able to effectively clamp this between the headstock and the tailstock in order to run a longitudinal current through it. So we use that rod in order to do that circular current, or sorry, circular field because of a longitudinal current. So it's often used to do things like gears, rings, tubes, etc. Your conductors, copper, brass, or bronze, most of them are going to be bronze. Okay, copper and brass you can use, but since they're fairly soft materials, especially when you start running a lot of current through them, they heat up, they tend to bend. So if they get, they're clamped under pressure and then you heat them up, they'll start to sag or bend in the middle, whereas bronze is less apt to do that. So we usually see bronze rods, that's what we have down there. And that current flow produces that circular magnetic field. And it magnetizes an area roughly 4 times the diameter of the conductor in the outer circumference of the part. Okay. So the bigger the part in relation to the conductor rod, the more you will have to turn it in order to make sure you magnetize the whole part. So sometimes you have to do multiple shots, multiple magnetic tests by rotating the part on that rod. So it's set up like this. Here's a gear in here. Or if we look at kind of drawings of the fields, this is what we end up with, that current running through the rod, creating those circular magnetic fields. And so we can find these longitudinal cracks. But again, you won't see a crack going transverse here. To do transverse, we'd slide the ring over and we'd magnetize this part the other direction. Okay. Using that central conductor, in this case, in a tube versus like a gear that we have here. And this is that diagram, kind of a cross-section diagram showing how that magnetism forms in terms of how do we figure out how many times we may have to rotate our part, or how many degrees do we have to rotate our part each time in order to effectively magnetize the entire part. So we have to look at our diameter of our rod here. This is that bronze conductor shown in here. Central conductor. And the magnetic field, the circular field that forms around this, when we run current through it, will effectively magnetize an area approximately 4 times that rod's diameter. And so what you have to do is you look at the point where the rod is touching here, the vertical point, and you take the diameter, you can go 2 distances to the left and 2 diameters to the right. And you can see like a ring like this, it's going to magnetize a little bit further on the inside surface than it is on the outside surface, because the outside surface, the circumference is longer on the outside than it is on the inside. So again, this top part, this 4 diameter, we take the diameter here, you go 1, 2 to the left, and you go 1, 2 to the right in order to calculate how far that is. So you can see you probably want to use the largest to minimize the number of times you have to turn the part. What we would have to do then if we want to inspect the rest of this is we have to rotate the part and run the inspection again. Rotate the part, magnetize it with particles, inspect it, rotate the part, magnetize with particles, inspect it. You don't have to demagnetize it on each step. Okay, that residual magnetism from before is going to be, it's not going to hurt anything. But you typically want to use the largest rod you're able to fit within a part. If it has a bigger opening, we have different diameter bronze rods down there. And the larger the rod you use, the less times you have to turn that. Now sometimes what you get is a bigger gear with a very small central hole. You have to use a fairly small rod. There you have to rotate it quite a few times. So you just got to kind of keep that in mind. So, one of the things you'll have to do as part of your lab, and as well know how to do, is how do you calculate this? How many times do we have to turn this? Okay, so we'll do a quick exercise here based on this. Let me grab a marker. So, and then just pause here. I'll keep it running. So if we have a central conductor, so small d, right, equals a 1/2 inch. That marker is terrible. Try this one. So I'm going to have you guys figure this out real quick. There we go. D equals a 1/2 inch. Okay. And now I am going to, typically, we don't know what this circumference is. You know, we can't directly measure a circumference most of the time unless you have a piece of string and a ruler. Whereas we normally have, you know, calipers and that kind of thing that we can use to find the large diameter. So if, let's say the diameter of our tube, and I'll call that, usually it's written as large D, and this is the outside diameter. So the outer, you know, from the outside to the outside here, the OD of the part equals 3 inches. Okay. How many times do we have to turn this part in order to magnetize the whole thing? I want you to do the calculations real quick. Let's see what you can come up with. Okay, so if we want to go through the calculation process with a 1/2 inch diameter rod, a 3 inch outside diameter part, okay, what do we have to do first? What do you think we have to find first? What do we need to know? We need to know the circumference of our part. We'll call that C. What does C equal? What's that? Yep, pi times diameter, so that equals roughly about 9.5. What's that? 9.42. Okay, I was close. 9.5, 9.42. Okay. 3.14 times 3, right? 9.42. Okay. Now, so it's 9.42 inches outside diameter, or outside circumference, excuse me. So now we want to know how many times do we have to turn the part? What do we have to do to figure that out? We got to figure out how far it's going to magnetize. So 4 times the diameter. So 4 times D equals 2 inches, right? 2. Right? 1/2 times 4, 2 inches. Okay? So how many times do we have to turn it? How do we figure that out? And we'll call that rotations. Not rotations, but segments, I guess. Typically we call it, how many times do we have to rotate it? We have to pick it up and rotate it. How do we figure that out? How many times? What do we do? Divide C, which is the circumference, 9.42 divided by 2, right? Gives us, let's see, 4.5, 4.71, roughly. Okay. 4.71. Now, it's going to be really hard to like turn apart 4.71 times exactly, right? So typically we round it up. No matter what, we're going to round it up. Even this isn't your, you know, you don't round down. If you round down, you know, if it ends up being 4.4 and you round down, you're going to miss 0.4 of that part, right? You're not going to. So it's better to overlap slightly each time than risk missing a little pi piece of it. So 4.71, we would want to make 5 rotations or 5 segments. Okay. So we're going to have to take our part and we're going to have to turn it 1/5 of the way and do it again, and turn it another 1/5 and do it again, and turn it another 1/5 and do it again. How many degrees do we have to rotate each time? How do we find that? How many degrees do we rotate each time? 360 divided by 5. I heard it somewhere out there. 3, that should be a 60. What's that? Someone with a calculator, that's 75? 72? Okay. So you're going to rotate it about 72 degrees each time, give or take, okay? Remember, we got a little bit of wiggle room there because of that overlap each time. So sometimes this works out nice and easy where we got to rotate like 4 times. You do 1, 2, quarter, half, full. Sometimes it's a little more complicated where you got to do 5 rotations, right? So again, you can see where if we had a bigger rod, say our rod was a 1-inch diameter, this would be 4, 9.42 divided by 4, we'd end up with 3 rotations. We'd do it about a third of the way each time. Okay. So that's, one of the things you'll need to do in your labs as well as on any kind of exams is figure out how many rotations or how far do we need to rotate apart when we're doing center conductor method. Okay. Another method for performing magnetic particle inspection that we won't be doing, but that we need to know about is portable magnetic particle. And this is using something called a yoke or prods. There's 2 different devices that provide our magnetization. So rather than having a fixed bench, we have a portable yoke or a pair of prods plug into the wall. And they're basically a portable electromagnet that you can bring up to your objects. So these are often used for in-service. Say you need to check like a steel portion of a landing gear leg, and you don't want to pull the whole landing gear out of the airplane to take it to a test bench, right? We can use these kind of things. So these can be done with dry powder, essentially a dust you use a little like puffer bulb. I'll show that in a second. Or there are aerosol prepared baths. Basically, it's a suspension of those same particles in an aerosol can. It's an oily, it's almost like aerosol particles inside of a WD-40 kind of liquid. And that gets sprayed onto the part where you're there. So these can be visual or fluorescent. So with our test bench, we're typically always using fluorescent particles just because we're in a controlled environment. We can shut the lights off. We have black lights available. When we're doing this out, in the field, we don't always have that luxury. Sometimes we can. Sometimes we can dim it or we can put up like a tent type area. And when I say a tent area, when we do portable fluorescent stuff, a tent was a black trash bag that we just kind of drape over ourselves. Then it would block out enough of the light. But you can also have visual powders, where the magnetic powders are coated with a bright or some kind of a color that provides a contrast. So here's an example of a pair of prods. So you can see this, in this case, this portable unit. Now this is a big heavy duty one for doing things like steel plate. But essentially all it is it's sending power down these 2 contact points and running it through this piece of metal that it's on. And it's going to develop a magnetic field around the base of those 2 prods. So we're running a current here through a part. Okay, that's a set of prods. A yoke looks something like this. Okay, this is the entire thing versus the prods where they've got this kind of power pack transformer over here. This yoke, this cord right here goes off and just plugs into a wall outlet. And it creates a magnetic field between the 2. Now, this one, the difference is the prods are going to actually run a current through the part. And that's going to create a magnetic field in the part. And that creates a magnetic field that looks like this. So when you have 2 prods running a magnetic field or running a current between them, you get kind of 2 circular magnetic fields. They create they look like ripples on a pond. Compared to the yoke, this does not actually run current through the end. It's basically just a big electromagnet. And so the magnetic field is jumping from one end of the yoke to the other. And that creates a more linear magnetic field between the 2. Okay, so again, to compare, you get the circular magnetic field between the prods where a current runs from one prod into the part and out back up the other prod. You can see current flow. Whereas a yoke basically is just a magnetic field. It generates a magnetic field. It does not actually send current through. Yeah. This one, usually there's some kind of an adjustment. I don't know where it's shown on here. There's a dial right here. So there's a dial here, and then he's going to have probably a trigger or a switch here on the handle to turn on and off. So you adjust that current right there, right on the top. Whereas these, you can buy adjustable ones or you can buy ones that aren't. So So the coil in here, the current carrying coil is up in the top. And then you've got iron, basically iron ends. And these are, they're riveted iron plates, so you can actually bend these around to make them wider or narrower. But you can spread them out or put them together closer depending on how you want to do that. These often don't have, because you're not running the current through the part, there really isn't much of a risk of overheating it. So they pretty much just have a button you press to turn it on. Most of the ones I worked with, they did not have any kind of an adjustment for power setting. What you can do is they don't actually have to touch the part, right? That magnetic field is going to form there. So if you're touching the part, that's going to be the strongest magnetic field. You can always pull it away from the part a little bit, and the magnetic field actually going in the part is going to be a little bit weaker. So the distance from the ends of these, yoke fingers, I guess, can affect what the field strength is in the part that you're testing. These also, we had another use for these. We talked about how we have to demagnetize parts when we're done. And we demagnetize parts by putting them in a collapsing field. We'll look at how that works in a minute. We would often use these to demagnetize parts on the airplane after something like a lightning strike. So when lightning hits an airplane, travels through, that's a strong current that runs through the aircraft. And steel parts on the aircraft, when that current runs through them, can become magnetized. The ones that were particularly prone to that were the landing gear legs, the steel components on the landing gear. And so after a lightning strike, we would have to go around with that Gauss meter and check certain areas of the plane to make sure, and if we detected magnetism, we would bring one of these yokes out, and we'd have our landing gear leg sitting there, and we'd bring our yoke like this, we'd hit the button to turn it on, and then we'd pull the yoke away. And you do that a bunch of times, and it basically scrambles those individual atom fields and demagnetizes that landing gear leg. It also is things like windshield frames. We'd have to do the windshield frames so that it wouldn't mess up the whiskey compass that was at the top of the windshields. If there was magnetic hardware in the wing area, flap tracks, the tracks and the hinges for the flaps and the ailerons, those could get magnetized. And those are out near the flux gates for the navigation systems that sense the Earth's magnetic field. You don't want to have a big magnet right next to the sensor that's trying to sense the weak magnetic field the Earth produces. So, this had multiple uses. You'll see these. We never actually used them to perform MPI at any of the facilities I worked at. They were just there for demagnetizing the airplane whenever they got hit by lightning. We didn't have any prods either. Again, most of our stuff that had to be MPI were things like aileron bolts and hardware that connected flight controls, the rollers for the flap tracks, like the little rollers the flaps ride on, the landing gear components when the landing gear are being overhauled and they're disassembled, and that kind of stuff would be sent to either our back shop at the airline, or oftentimes we'd send them out. Duncan Aviation at their Lincoln facility, they do a lot of third-party contracted NDT and other suppliers like that, where we'd get a bolt would come back that had been in service, it had been tested, it would come back with a new 8130 saying it was airworthy or serviceable to put on the aircraft. So those are our different methods for performing MPI and the different fields that they produce.